Hello. So in this video, I want to introduce a model for friction and talk through what that model is meant to describe. And then towards the end, show you a demo of what friction looks like in practice. So first of all, when we say friction, what we're describing is the result of an interaction between two surfaces. So if imagine I have the ground right here, and I put a box on the ground just for simplicity of thinking it through. If I try to push on this box, then I'm going to get friction. So if I apply a force, so this is my force that I'm applying to the right this way, there's some amount of force that I could apply where the box wouldn't move because the box is being held in place by its interaction with the ground. I'll draw that this way. So there'd be some frictional force here. And in the case that the box isn't moving, I'm not applying enough force to break the friction that's holding this box to the ground. We'd call that static friction. And the static friction is what we call the friction that exists when two surfaces aren't moving relative to each other. So let me write that out. So static friction exists when two surfaces aren't moving relative to each other. So that is, if the box is stationary relative to the ground here, and I'm applying force, but the box isn't moving, there must be some static frictional force that's preventing my force from accelerating the box. The model that's commonly used for this is to say that there's some static friction, fancy F sub S, which is going to be less than or equal to some maximum value, which is given as mu of S times N. So let me denote what these are. So this is the frictional force. So this is static friction, frictional force. The big N here is the normal force between the two surfaces. So that is in my diagram, I guess I can use a different color here. So there'd be some normal force on this box, which would be the force of the ground pushing up the box. There'd also be a normal force that the box applies on the ground, which is equal and opposite. That's what this represents in this context. So the frictional force, or the maximum value that the frictional force can have, scales linearly with the normal force in this model. This thing here, that's called the coefficient of static friction. It's a mu, that's a Greek letter. It kind of looks like a fancy U, but it's a mu. And this contains tons of information in it, but typically you find it experimentally. So it's kind of important to understand what the coefficient of static friction is. So the coefficient of static friction tells you when you push two surfaces together, so if you push this box into the ground and you create more normal force, then you get more potential for static friction here. But the amount of friction scales linearly with the normal force, and that scaling factor is the coefficient of static friction. So you can imagine what kind of things would affect the coefficient of static friction. If that coefficient is higher, that means friction is stronger. If that coefficient is lower, it means friction is weaker. So things that are smoother will probably have lower coefficients of friction. If there was water on this surface, probably the coefficient would be less. If there was oil, it would be even less, and so on. So that's a property of the two surfaces together, rather than a property of any particular material. It's a property of an interaction between materials. So I'll write that out. The coefficient of friction depends on both materials and what they're shaped like and all that kind of stuff. So I guess I'll say on the specific objects in contact. And this is something you've got to find out empirically. So you have to find this through some experiment. The part of the reason why you have to find this empirically is because this model for friction, Fs is less than or equal to µs times n. This is a model that's pretty good, but it's meant to describe a whole host of things, and it's not a perfect model. It's kind of like the best we can do with an interaction that's as complicated as friction. Because if you think about it, what affects friction? So what causes friction? So in this case, what causes the friction here? Well, I guess surface roughness. So if you had two surfaces that were rough, imagine that if I zoomed in on a section of the box above, the box looks actually like this. It's not flat, right? It's jagged. So this is some section of the box. And then if I zoomed in on a section of the ground looks like this. So this is a section of the ground. And if you imagine, sliding this box along the ground, you're going to get some sort of resistance to motion just based on these little jagged peaks and troughs where things catch on each other. So that's one thing that can cause friction. Another thing that can cause friction is deformations in surfaces. So surface deformations. So an example of thinking this through, imagine that I've got my box, and maybe it is a flat box. So I've got some section of the box here, but now the ground is soft. Maybe it's it's a swamp, or it's made of grass and the grass is wet or something like that. So when I push this box into the ground deforms under it like this. And now it's kind of like I've got my box in a little deformed bit of ground that just sort of continuously deforms as you move the box along it. So now you've trapped your box in this little valley, kind of, and it's going to be difficult to push it out. So you get a little bit of friction from that, deformations in the surfaces. A third thing that causes friction, intermolecular attraction, or I should say interactions. So if I put two surfaces together, there's going to be some interaction between the molecules or the atoms of those two surfaces. Exactly how that works is going to be really hard to figure out. But you might be able to do it empirically, and that'll depend on the specific things in contact with each other. All of these things, these sort of three causes, and we could maybe try to think through other potential causes that aren't described by these three, but these are three really big ones. All three of these things are what we're trying to describe through this model. And all three of those things are extremely complicated. So this model, for most things that we'll encounter, is pretty good, but it's not perfect. And it's not intended to be perfect. It's something that's intended to be good enough for us to work with and make predictions about how systems work. So I want to talk about a slightly different kind of friction too. So this was static friction at the top. So for kinetic friction, so kinetic friction would be if I have maybe the same situation, and I'm pushing on the box, but it's moving already. So either I've pushed it hard enough that I've overcome the static friction that was holding the box in place, or it was moving already and I'm just applying a force to it, let's say, to keep it accelerating. Then if this is moving, how do I give it some velocity? We'll say there's some velocity in this direction, velocity to the right. There's going to be some frictional force opposing that motion for all the reasons described above. All these factors, the roughness, deformations, and interactions between the surfaces, those are still creating friction. But as it turns out, there's a difference in how strong friction is when you have two objects sliding relative to each other versus when they're static with each other. At least in most cases, there is a difference. And the model that we use for that is kinetic friction is equal to, not less than or equal to, but equal to mu k times the normal force. So again, I'll label these. So this is kinetic frictional force. The form here looks really similar, but there are some important differences. This is the coefficient of kinetic friction. And again, this is the normal force between the two surfaces. Same as before. If we compare the two equations, so if I go back up to static friction, there's an inequality here. That means that if I'm pushing less than this amount, static friction will be able to hold the block in place. But it wouldn't make sense for static friction to apply a constant force, no matter how much force you applied, because then you could get into weird situations where you would predict that friction would accelerate the box in the opposite direction of your push, which wouldn't make sense. So this tells you a maximum value. And if you push harder than this maximum value, then you overcome the static friction and the box starts sliding. If you get into the regime where the box is sliding, then this says that the kinetic frictional force is just always the same value. That's what our model says. So if the box is sliding, you just get the same force all the time. There's no change in the value of the kinetic friction based on the velocity. There's no change based on how hard you're pushing. It's just a constant value. And that model turns out to work pretty well, which is really nice. Okay, so let's do a little example here. So let's say I have a problem where I've got this 2 kilogram box sitting on a table and I apply force, but the box doesn't move. It only starts to move when I apply 10 newtons of force. So the question is, what's the coefficient of static friction? So we have this model for static friction where the static friction is less than or equal to this maximum value. If we're told that the box begins to slide when we apply 10 newtons, then we know that right when we're applying 10 newtons, then that's kind of the maximum value. The maximum amount of static friction that we can have is 10 newtons, because if I apply that much and just a little bit more, then the box starts to accelerate and I break static friction. So we know in this case that the static friction is equal to 10 newtons. And that has to be the maximum value. And so we also could figure out what the normal force is. So if we know the weight is mg, which we'll approximate g as 10 here. So let's say the weight is 20 newtons. And we're not accelerating up or down, then the normal force also has to be equal to 20 newtons. So then I can say that mu s times 20 newtons is equal to 10. So mu s equals 0.5. There are no units to the coefficient of friction. You'll notice that it's a ratio of two forces. So it's a ratio of the normal force, of the frictional force and the normal force. So it's newtons over newtons, which is a unitless number. So there's no units to this. That's a way you can start using frictional force. There's a lot more examples we could do, and there'll be problems related to this to do. But I want to give you a little experimental look at how force over time works with friction. Give me 1 second to pop over to that. Okay, so I've got this little demo here. What I've got is, this is a little cart. There's some cork on the bottom here. I put a couple of weights in here just to make it heavier. But basically, this is just a box, and I'm gonna slide along this table. This thing is a force sensor. There's a hook on the end, and when the hook experiences a force, this will output the force sampled at whatever sampling rate I want. in SparkView. And I'm going to show you that data as I pull on this. So what I'm going to do is that the experiment I'm going to show you is I'm going to just apply a consistently increasing force by pulling on the force sensor, which pulls on this cart. And then if I apply enough force, the friction breaks and it starts to slide. So what I'm going to show you is how, as I pull harder, how the force applied changes over time and how that maps onto the actual motion of this cart. So let's take a look at that. Okay, so I think you can see SparkView and also video at the same time. So you can see what I'm doing with the cart and the force sensor and compare it to what's happening with the force graph over time. So to give you a sense of what this looks like, I'm just going to do sort of a dummy run to start. If I hit start and I pick up the force sensor and pull a little bit, you can see that the force goes up. I'm applying more tension force actually in the string right here, and it's pulling on the cart more and more. I haven't pulled hard enough yet to break the static friction. Nothing is moving. If I apply less force, you can see the force decrease. So there's going to be some threshold here where I'll apply enough force to break the static friction, and that's what we're going to look for. So let me stop this and start a new run. So let's try to do that. So I'm just going to try to apply a steadily increasing force here, and we'll check to see what happens when the static friction breaks, if it breaks. So let's see. So I'll pick this up. I'm going to apply a steadily increasing force, and then at some point it breaks. And if I continue to drag it kind of at a constant velocity, you can see that. So let's look at that for a second. You can see that I was applying constant force all the way up to this peak. So that peak corresponds roughly to the maximum static friction value. Kind of like in the example problem that we just did, where if I apply a certain amount of force and I need that much force to get the thing moving, that tells me what the maximum value of the static friction is. So from this value, sort of up here near 16, I could maybe calculate what the coefficient of static friction was if I knew the mass of the cart that I was using. As soon as I overcome the static friction though, I end up with a big decrease in the force that I'm applying. I was just trying to pull it at constant velocity. So if I'm pulling it at constant velocity, the force that I'm pulling with roughly corresponds to, well, if I actually am pulling it with constant velocity, then the force that I'm pulling with should be the same as the kinetic frictional force. But in this case, because I can't do that perfectly, it'll be roughly correspondent to the kinetic frictional force. And you can see here that the value of the kinetic frictional force is less based on that analysis than the maximum static friction force. And if you think about it, that means that the coefficient of kinetic friction has to be less than the coefficient of static friction, which is quite common for most materials in contact, although it doesn't have to be true necessarily. So that's an example of what it looks like when you actually start pulling something, and how static friction force changes over time, how kinetic frictional force compares to static frictional force. So I hope that was helpful for a little brief introduction to this simple model of friction that we're using, and I'll see you soon.